Hello, I'm Jack Baker. This presentation will provide you with an introduction to the conditional mean spectrum. The motivation for this talk is that we're interested in understanding what exactly probabilistic seismic hazard analysis tells us about future ground motions at our site, and then we're interested in learning how can we best use that information to select appropriate ground motions for structural analysis. The outline of the presentation is as follows. First, we'll discuss briefly probabilistic seismic hazard analysis and the uniform hazard spectrum. Those are both important background concepts for understanding the conditional mean spectrum. Once we have that as background, we'll take a brief look at what are the properties of ground motions associated with high amplitude response spectra. And using that idea, that'll motivate the development of the conditional mean spectrum, or the conditional spectrum, a slight alteration on the conditional mean spectrum. Once we have that developed, we'll look a little bit at the implications in terms of ground motion selection and structural analysis, and then I'll conclude with a few resources that you might find useful if you're interested in pursuing the use of this concept. Okay, as background, the seismic hazard information that you might be most aware of or most familiar with is the seismic hazard maps produced by the U.S. Geological Survey, and these map design peak ground acceleration or spectral acceleration values with a specified probability of exceedance in some time window. Another way of looking at that is for a specific site located somewhere on the map, we can actually look at spectral accelerations of all amplitudes at a particular period. So in this lower left figure, I've plotted spectral acceleration at 1 second versus the annual rate of exceedance of each amplitude, that spectral acceleration. And what the map up top shows is just the amplitude at some specific rate of exceedance associated with that target probability. But we could choose any other rate of exceedance and find also an associated spectral acceleration amplitude. Another piece of information that goes along with that rate of exceedance of any particular spectral acceleration amplitude is what's called deaggregation. And this figure shows for a given spectral acceleration amplitude, occurrence of ground motions having that amplitude, what is the distribution of magnitudes and distances, and also a third parameter epsilon? What is the distribution of these three parameters associated with ground motions having that spectral acceleration amplitude? Okay, so we're going to assume all of that's available, and I'll assume you have some level of familiarity with any of those three concepts. Okay, another way that this seismic hazard information is combined frequently for use is in construction of the uniform hazard spectrum. So over on the left here, I've got two plots of site-specific hazard curves for a single site. The top left figure shows the hazard curve for spectral acceleration at 0.3 seconds. The bottom figure on the left shows the hazard curve for spectral acceleration at 1 second. And at any given annual rate of exceedance, we can pull off the spectral acceleration amplitudes at these two periods, and those are marked with the symbols on those two left plots. And we could plot them both on a third plot, which I have plotted at the right. So this is spectral acceleration versus period. We could fill that figure in with additional spectral acceleration amplitudes at other periods and build a complete response spectrum. This is what's called the uniform hazard spectrum, and it has that name because at any period on this plot, the spectral acceleration amplitude shown in that spectrum has the same annual rate of exceedance as all of the other spectral acceleration amplitudes on that plot. So we have a consistent rate of exceedance at all periods. That's a useful concept, and it's widely used today. But one thing we want to emphasize here is that this is just a collection of spectral acceleration points from a whole series of analyses, and it doesn't say anything about the simultaneous occurrence of those spectral amplitudes in any single ground motion. It's just a collection of points. There's nothing about simultaneous occurrence. That's an important concept. We'll come back to that later. Okay, let's look at how that uniform hazard spectrum plays out for a real site. Here I have plotted the uniform hazard spectrum for Riverside, California, as obtained from information provided by the U.S. Geological Survey in the 2002 version of their maps. So for periods between 0 and 2 seconds, they provide the amplitudes of spectral accelerations that have 2% probability of exceedance in 50 years. Let's say we're interested specifically in the spectral acceleration at 1 second. That's an amplitude of about 0.9 g in this case. And we can do deaggregation, that's information provided by the U.S. Geological Survey, to tell us what's the distribution of magnitudes, distances, and a third parameter epsilon. What's the distribution of those three parameters given spectral accelerations at 1 second having a 0.9 g amplitude. We see there's a small contribution at a magnitude of 8 and a distance of 20 kilometers. That's corresponding to the San Andreas Fault, located about 20 kilometers away, that occasionally produces magnitude 8 earthquakes, and that has some contribution to ground motions at our site with the 0.9 g amplitude at 1 second. There's a bigger spike in approximately a distance of 10 kilometers with magnitudes of about 7. That's from the more nearby San Jacinto fault, because that's close by and also active in this particular case for this particular spectral acceleration period and amplitude. That has a greater contribution than the San Andreas fault. So we can see which types of earthquakes are likely to be causing these high amplitude ground motions at our site. Also, you'll notice highlighted in here, I've noted that the U.S. Geological Survey provides the mean, magnitude, distance, and epsilon values. We see here that there's a mean distance of about 12 kilometers and a mean magnitude of about 7 for this particular site corresponding to that San Jacinto fault. So let's go back over to our response spectrum, and here I have plotted the predicted median spectrum for a magnitude 7 event at a 12 kilometer distance. So that's what, in this case, the Bohr and Atkinson ground motion prediction model would tell us. Here's what we would see in a median sense in terms of spectral acceleration amplitudes from that event. But that's much lower than the 0.9 g spectral acceleration amplitude that we've been discussing. So why the big discrepancy here? And the answer comes from this third parameter back over in the deaggregation plot it's indicated by the color coding of the bars. And that's the epsilon parameter. And epsilon tells us of the ground motions with the 0.9 g amplitude, how many standard deviations larger than the median prediction are these ground motion spectral accelerations. And in this case, we have an epsilon of 2, saying that we are about 2 standard deviations larger than median predictions on average with these high amplitude ground motions. So if we come back over to the figure on the left, I've now added a third line. This is the median plus 2 standard deviation prediction from the Bohr and Atkinson model for magnitude 7 ground earthquakes at a distance of 12 kilometers. So the key point to take away here is that our uniform hazard spectrum, especially in seismically active areas, is not the spectrum associated with average ground motions from scenario earthquake events in the region. There's actually much larger in amplitude, in this case, 2 or 3 times larger in spectral acceleration amplitude than that median spectrum. And so we're looking at kind of the large nearby earthquakes as well as very strong spectral accelerations given the occurrence of that earthquake. And that's important. So let's look a little bit more. Now let's look at some recorded ground motions and see if this plays out. And here's what I'm going to call it, the epsilon effect. And it's a very real phenomenon. So plotted in black in the solid and dashed lines are the same median spectrum and median plus 2 standard deviation spectrum that we were just looking at on the previous slide. Plotted in green are response spectra from recorded ground motions that had approximately a magnitude of 7 and approximately a distance of 12 kilometers, plus or minus a little bit of variation to get us about 20 ground motions here. And what you can see is that solid black line, the median prediction, seems to be passing approximately through the average values of these response spectra. So that's what we would expect. Also, we see that at any given period, there are 1 or 2 ground motions that have spectral accelerations as large as this median plus 2 standard deviation spectrum. We have very wide variation in these spectral acceleration amplitudes. It's not difficult to find ground motions with factors of 5 variation in their spectral acceleration, even though they came from approximately the same magnitude and distance. So this variation and this need to model larger than median ground motions is a very real phenomenon. To make this example a little more specific, going back to our spectral acceleration at 1 second, I've also highlighted in blue the response spectrum of one particular ground motion that has about the 0.9 g amplitude at 1 second that we were originally identifying in our uniform hazard spectrum. So there are ground motions that have that high amplitude. But what's interesting to note here is that in this particular case, and this is a phenomenon that we see more generally, that response spectrum is not, the blue response spectrum of the recorded ground motion is not 2 standard deviations larger than the median at all periods. It is at a few periods, but at other periods it comes back down closer to the median spectrum. And so using that uniform hazard spectrum, while individual amplitudes at individual periods we could certainly observe, it's very unlikely that we would observe those high amplitudes at all periods within a single ground motion. And so that motivates this conditional mean spectrum that we'll discuss for a while. In order to get there, let's look at epsilon values at multiple periods. So again, I said epsilon was the number of standard deviations that a particular spectral acceleration differs from the predictive model. And this is all a number of standard deviations in terms of log spectral acceleration. So over on the left here, we've got the computation equation that epsilon is equal to log of the observed spectral acceleration minus mean of the log of spectral acceleration denoted mu. And that's going to be a prediction by some ground motion prediction model or attenuation model, and they're typically a function of magnitude and distance, the period you're interested in, and other parameters like soil conditions and whatnot. So we'll take the observation minus the mean prediction divided by the standard deviation of log spectral acceleration. That's another parameter provided by the ground motion prediction model. Okay, so to illustrate that, over on the right I've got the that same ground motion that we were just looking at, and so in blue is plotted the real response spectrum. In solid black is plotted the median record spectrum, which is the exponential of that mean log spectral acceleration in the equation at the left. And then we have bands of plus or minus 1 or plus or minus 2 standard deviations. And so we can count how far away is this particular observed spectrum from the median predictions at a particular period. So at 1 second, we were about 2 standard deviations larger than the prediction, actually 2.3 to be more specific. If we go over to 2 seconds, we see that we're 1.4 standard deviations larger than the median prediction. And on the left at 0.2 seconds, we were 1.2 standard deviations larger than the median. So let's keep those numbers in mind. We could do the same calculation with a large library of ground motion. So I did that with several hundred ground motions. And here's a plot of what things look like. So for this big library of ground motions, I have a plot here of, on the x-axis, epsilon values at 1 second, and on the y-axis, epsilon values at 2 seconds. And each point in this plot is the observation from one particular ground motion. Our ground motion we were just looking at had an epsilon of 2.3 at 1 second and 1.4 at 2 seconds. And so we can see those values if we plotted those at 2.3 and about 1.4, we get this particular ground motion right here. And other ground motions have higher or lower epsilon values. And we see that those epsilon values tend to move together, so we tend to have either high epsilon values at both periods or low epsilon values at both periods, but it's not a perfect dependence between these two values. I've also got plotted here histograms off the x-axis and the y-axis showing just individually how often do we observe different epsilon values. And these things are well modeled by normal distributions having a mean of 0 and a standard deviation of 1. The mean of 0 and standard deviation of 1 comes from the normalization that we did earlier. So on average, we're not under-predicting or over-predicting the observed spectral accelerations. Okay, so now the question would be, my deaggregation told me that I had an epsilon value of 2 at a period of 1 second. So what would that tell me about my epsilon values at 2 seconds? And we can actually do some math if we make the assumption that these things have a joint normal distribution. And it turns out that the mean value of epsilon at 2 seconds is equal to the epsilon value at 1 second multiplied by the correlation coefficient between these observations at these two periods. And so in this case, the data has the epsilon 1 second and epsilon 2 second data has a correlation coefficient of 0.75. So we could say that the mean epsilon at 2 seconds, given an epsilon at 1 second of 2, would be 1.5. And similarly, we can do a calculation of the standard deviation, which would tell us kind of how wide is our variability in terms of epsilon values at 2 seconds, given a specific value of epsilon at 1 second. In this case, that standard deviation would be 0.5. We would have reduced the uncertainty relative to the original distribution of the epsilons at 2 seconds. Okay, we could do that same calculation at other pairs of periods. So on the left, I have the data that we were just looking at, epsilon at 1 second versus epsilon at 2 seconds. On the right, I have the data showing epsilon at 1 second versus epsilon at 0.2 seconds, plotted from this large library of ground motions. So here we see that epsilon at 1 second and 0.2 seconds data is not as highly correlated as the 1 second versus 2 seconds data on the left. And so that's going to have mean that the knowledge of epsilon at 1 second doesn't tell us quite as much about what's going on at 0.2 seconds. So in this case, the correlation coefficient is 0.44. So the mean epsilon at 0.2 seconds is 0.44 times the epsilon at 1 second. So if we had an epsilon of 2 at 1 second, that would mean that our mean epsilon at 0.2 seconds would be 0.88. Okay, so we could repeat this whole process at all periods and come up with mean epsilon values at all of these periods conditional on the knowledge of epsilon at 1 second. Okay, so coming back over to our previous figure here, in black I've got that median spectrum, and then those epsilon values we were just looking at are going to tell us how much larger or smaller we are than that median spectrum. So at 1 second, we said we were 2 standard deviations larger than the median, that epsilon of 2, that came from our deaggregation information. At 2 seconds, the epsilon value we said was going to be 0.75 times the epsilon at 1 second because of that correlation coefficient. So we'd have an epsilon of 1.5. And then over at 0.2 seconds, we have an epsilon of 0.888. We could fill that in for all of the other periods, and counting that many epsilons up from our median spectrum gives us that dashed red line. And we call that the conditional mean spectrum because it's conditional on the spectral acceleration at 1 second and all the deaggregation information about the epsilons and then the magnitude distance that gave us our original median spectrum. So conditional on all of that, what would we expect the epsilons to be at the other periods in their mean sense? So that's our red spectrum. And reassuringly, the blue response spectrum of the recorded ground motion that actually came close to satisfying all those observations falls, along a pattern very similar to this red conditional mean spectrum. Note also that this conditional mean spectrum is significantly lower than the dashed black line, which is our median plus 2 sigma spectrum, and was something kind of similar to our uniform hazard spectrum. So that's again an indication that taking that uniform hazard spectrum, which is similar to that dashed black line, if we were thinking about that as a typical ground motion response spectrum, we would be quite conservative potentially. Okay, taking off a couple lines here, let's add one more set of lines here in the dashed thin red lines. Well, here what I've done is I've plotted a conditional mean spectrum plus or minus a conditional standard deviation, where the conditional standard deviation was the other value we were computing from the scatter plots of epsilons. And so when the period is very close to 1 second and the correlations are high, our conditional standard deviation is low. When the period we're interested in is far away from 1 second and the correlations are lower, then that standard deviation gets larger, and we see this bound getting a little more spread out. And so that's capturing the variability around the conditional mean spectrum that we would expect to see in ground motions that had the specified magnitude, distance, epsilon, and spectral acceleration at 1 second. Okay, so that's the conditional mean spectrum calculation. Once we have computed that as a target, we could select and scale ground motions to match that conditional mean spectrum. And we could do that in a couple ways. On the left, I've got a figure showing that conditional mean spectrum plus or minus the conditional standard deviation we just looked at. And then I have plotted the response spectra of ground motions that match both the conditional mean and the conditional standard deviation. So at any given period, if we looked at the mean and standard deviation of the ground motions having these response spectra, or if we looked at the mean and standard deviation of the response spectra, that would match the mean and standard deviation from these conditional spectrum calculations. So that would catch both the kind of trends, the mean trends, and the variability we expect in those ground motions. On the right, I've got a slight perturbation of this, which is to select ground motions whose response spectra just match the mean only, so just match the conditional mean. We could do that selection by simply searching through all of the ground motions in a library, scaling them so that they match the target spectral acceleration at 1 second upon which all this analysis was conditioned, and then just selecting the 10 or 20 or 40 ground motions that most closely match that target individually, not worrying at all about the variability. So those are two different options. The left one I think today we'll be calling the conditional spectrum, and on the right this would be the conditional mean spectrum because we're focusing just on the mean values here. And both of those could be options for ground motion selection. We can discuss later what the trade-offs would be there. Okay, so if we were to do that, here's what a ground motion selection might look like. So this is at that same Riverside site that we looked at the initial hazard analysis for, and this is plots at 4 different probabilities of exceedance. So in the top left, we have the 50% probability of exceedance in 50 years, spectral acceleration at 1 second, and the deaggregation associated with that is that the mean causal magnitude is about 7, the mean distance of these earthquakes is about 15 kilometers, and the epsilon is only 0.6, so a smaller epsilon, saying that these ground motions would be less standard deviations above the median than the earlier calculations we looked at. So a relatively lower spectrum. We could compute that conditional mean spectrum, shown in black, and then select ground motions to match the mean and standard deviation of that spectrum. Top right, we see the 10% and 50-year spectral acceleration, a little bit higher amplitude. The lower left, we see the 2% and 50-year spectral acceleration at 1 second. That's the case we were looking at just a moment ago. And then in the lower right, we have the 1 second, the 1% probability of exceedance in 50 years spectral acceleration. In this case, we've got a magnitude 7, a distance of about 12 kilometers, and an epsilon of 2.2. And as you look from the upper left down to the lower right and you see the amplitudes going up, you can notice that the shape of the response spectrum is becoming more peaked as we get down to the lower probabilities of exceedance. So as we go to larger and larger amplitudes at 1 second, we're getting to rarer and rarer amplitudes given that magnitude and distance, and it's less and less likely that other spectral accelerations at other periods would be comparably high. So we see the changing in spectral shape as we move in return periods. And in this case, because the causal magnitude and distance is not changing dramatically, this change in shape is primarily due to changes in epsilon. But if it turned out that the causal earthquake magnitude and distance was also changing with return period, then changes that would imply in terms of spectral shape, those changes would also be captured in these changing response spectra. And so we could select separate sets of ground motions at each amplitude to reflect those target response spectra. Okay, so keeping that in mind, we can anticipate what the implications would be in terms of structural analysis. So here I have plotted some probability of collapse versus spectral acceleration calculations from a previous study that I did with Kurt Hazelton, a professor at Chico State University. And what we did is select ground motions to match uniform hazard spectra at these different spectral amplitudes, and of those ground motions, identify how many caused collapse of this example structure. This was a mid-rise concrete frame building analyzed using nonlinear dynamic analysis. I won't get into the structural details too much here, but just to say that we were identifying the probability of collapse at these different spectral acceleration levels, and that's shown in black. Then at those same spectral acceleration amplitudes, rather than choosing ground motions to match the uniform hazard spectrum, we chose ground motions to match the conditional mean spectrum. And then we did the same structural analysis with those new ground motions, counted the probabilities of collapse, and got the blue curve. And what we see is that for a given spectral acceleration level, there's much lower probabilities of collapse when using ground motions selected to match the conditional mean spectrum. And we can see why if we go back to look at the previous plot that showed the conditional mean spectrum here in red versus something that's like the uniform hazard spectrum shown in the dashed black line up high. So we see that at the 1 second conditioning period here, both spectra have the same amplitude, but at longer periods, the uniform hazard spectrum is higher in amplitude than the conditional mean spectrum, and at shorter periods, it's higher than the conditional mean spectrum. And if we did all of this conditioning at the first mode elastic period of the building, which is a common choice, then comparing these two spectra would tell us that at those longer periods, the higher amplitude of the uniform hazard spectrum would imply kind of greater loading on the structure as its period lengthens due to nonlinearity and it softens due to damage. So we would excite the nonlinear response to a greater extent using ground motions that match the uniform hazard spectrum than we would if we had used ground motions to match the conditional mean spectrum. Over at shorter periods, the difference in amplitudes between these two spectra implies that ground motions matching the uniform hazard spectrum will excite higher modes in the structure to a greater extent than ground motions matching the conditional mean spectrum. So in both cases, we expect to see larger structural responses if we use ground motions matching the uniform hazard spectrum than the conditional mean spectrum, given that they both match at that elastic first mode period of the building. And that's exactly what we see when we look at this slide here, that we see kind of greater responses and, in this case, greater probabilities of collapse. I should mention that there's no need to restrict our calculations to conditioning using the first mode period of our building as the conditioning period, but that is a common choice today in practice to date. Okay, so we understand that there's potentially large implications on the structural response when we are identifying which response spectrum we should be using in selecting our ground motions. Thinking about what we've seen now with the conditional mean spectrum, here's a list of kind of positive and negative aspects of this conditional mean spectrum, especially relative to the uniform hazard spectrum, which is probably the most common target spectrum in use today. So a positive aspect of the conditional mean spectrum is it's a more realistic spectrum than the uniform hazard spectrum if we're conditioning ourselves on spectral acceleration at some specific period I'll call T star here. And that's because it's capturing kind of expected response spectrum rather than this enveloping spectrum that the uniform hazard spectrum is. The negative is that it's less widely available than the uniform hazard spectrum. Uniform hazard spectrum is quite easy to obtain from websites such as the U.S. Geological Survey's website, as well as standard probabilistic seismic hazard analysis software. An advantage of the conditional mean spectrum is that it's less conservative than the uniform hazard spectrum because it doesn't have this enveloping behavior, and that might be a very desirable feature if you're aiming to identify a kind of non-conservative structural response. A con is perhaps that it's a less conservative calculation than a uniform hazard spectrum, and if we're doing a building code requirements for new construction, maybe some degree of conservatism is called for, and that's not necessarily a bad thing. That would be probably the analyst's choice, whether they're willing or interested in having some level of conservatism in their calculations. So depending on circumstances, that could be a good or a bad feature. An advantage of the conditional mean spectrum is that we're using the deaggregation information on magnitude and distance and epsilon to identify the most realistic spectral shape for our ground motion. So we've incorporated all possible information that we obtained from the probabilistic seismic hazard analysis calculation. A con of that, though, is that this analysis is now structure and site specific. So I have to use deaggregation from a specific site. I have to know a little bit about my structure, maybe to choose the period in which I'm going to do my deaggregation. And as I move to different locations, I might need different ground motions. And that's different than, say, a code spectral shape that's going to be quite similar in perhaps as circumstances change and might not require reselection of ground motion. So there's a little more work here, but we have a little more realism in terms of the target spectrum that we're using for a particular site. An advantage of this conditional mean spectrum is that we looked for that example Riverside site, is that we changed spectral acceleration amplitudes, we changed the shape of our response spectrum. And that's consistent with our intuition. We expect that high amplitude ground motions are going to have different properties than low amplitude ground motions. And so having that shape change, and then thus having different ground motions at each spectral amplitude to match these different shapes, that's a more realistic analysis situation. However, it's an inconvenience. And so that changing spectral shape implies that we should have different ground motion sets for low amplitude ground motions and high amplitude ground motions. Again, there may be some additional work there rather than just taking a single set of ground motions and scaling them up and down in amplitude. So those are pros and cons. Whether the pros outweigh the cons in a given situation will probably depend on the goals of the analysis and the amount of work that the analyst is willing to do. There's some new calculations involved in this, both in kind of identifying the target response spectrum as well as in identifying ground motions that match that response spectrum. So to facilitate that, our research group, my PhD students Nirmal JRM and Ting Lin, have developed some software to aid in that selection. And what the software does, which is MATLAB source code, for those of you who have MATLAB, you run the source code and you input the information that you obtained from your seismic hazard analysis and your deaggregation. So you have to input the target spectral acceleration amplitude at a given period and the associated magnitude, distance, and epsilon that you obtained from your deaggregation. The software will then compute the target conditional mean spectrum and conditional standard deviation, and then it will select ground motions to match that target. So all of that algorithmic work that I described here is implemented in a code that performs those calculations. It's not necessarily a user-friendly or extremely well-documented code that's comparable to commercial software, but for those of you who are interested in implementing this, that may be a useful resource for you. Thinking of other resources for those of you who are interested in learning more about this procedure, the information I've presented in this presentation here is also available in a journal paper that'll be in press. It's currently in press, will be soon published in the Journal of Structural Engineering with the title given there on the slide. Also, the Peer Center at Berkeley has recently released a beta version of some web software interface that will allow you to compute a conditional mean spectrum and select matching ground motions. It's available at this URL here shown in the middle of the slide. It's a very user-friendly tool that has nice drop-down screens and visualization of the ground motions and things, and that's a tool that many of you might find quite useful. If you're interested in more kind of researchy version of this calculations, again, at my website, we have some publications documenting these procedures in more detail, and some research software, and by research software I mean MATLAB source codes, not necessarily so user-friendly and requires that you have a MATLAB license to use. But between these various resources, hopefully there's something that'll suit your particular needs if you're interested in learning more. Okay, to conclude, this conditional mean spectrum, if we were to summarize it in one sentence, I would summarize it as follows. It's trying to answer the question, what is the expected response spectrum associated with a target spectral acceleration at some conditioning period t star, and it's going to find that expected response spectrum using the magnitude, distance, and epsilon value that cause the occurrence of that spectral acceleration at t star, and we can find the magnitude, distance, epsilon from deaggregation information that's widely available today. So that's the expected response spectrum, this conditional mean spectrum. We can also find the conditional standard deviation that characterizes the variability in response spectra at all periods. And when we have both the mean and the variability, we might call it a conditional spectrum. It's no longer just a mean spectrum. And what we saw from those example calculations is the main implication that this conditional mean spectrum highlights is that when we have large amplitude spectral acceleration levels, by which I mean kind of epsilon greater than 0, or that implies spectral accelerations larger than median predicted spectral accelerations, these conditional mean spectrum, or conditional mean spectra, have peaks at the conditioning period t star, and as we move away from that conditioning period, the amplitudes die back down more towards the median spectrum, so we see these peaked spectral shapes. And this shape is a more realistic shape for high amplitude response spectra, and because of that, it's potentially a useful target spectrum for ground motion selection, and relative to the more widely used uniform hazard spectrum, the uniform hazard spectrum can be seen to be conservative. And because of that kind of difference in the amplitudes, we see generally that conditional mean spectrum matched ground motions tend to produce smaller levels of structural response in our buildings or in our engineered systems than ground motions matching a uniform hazard spectrum. That's going to depend somewhat on the sensitivity of the structure you're analyzing to different properties in the ground motions, but in some cases the difference can be quite significant. Okay, and finally at the bottom of the slide I have shown one more time the website of my research group, and if you're interested in more information you might want to stop by there and see the other documents and software that we provide.